Welcome to this follow-up on integration by substitution. We're on day 2 material from our outline, and they just get progressively more challenging, so let's go over some more examples. Let's take this one now in white. So we have the integral of secant squared theta, cubed root of tan theta d theta. Remember, we're trying to substitute in thetas and d thetas. We don't have to worry about getting rid of radicals or anything like that. So do you see an inside function and do you see an outside function? Well, let's start here, because this is the cubed root of something, but that something is another function onto itself. It's tan theta. If you notice an inside function, that's your u. But if you don't notice that right away, you may say, well, what's the derivative of secant squared theta? Well, I don't really know what that is, so I might not have it. Well, what about the other way around? Do I have the derivative of tan theta? Oh, yes, we do. The derivative of tan theta is secant squared theta. So if you remember what you do next on this u, you take the derivative, you get du. Then over here, you take the derivative of tan theta, which is secant squared theta, d theta. And now what we can do is this. We can substitute in this times d theta, because secant squared d theta equals du. And if that just confused you, I'm going to rewrite tan theta. I'm going to raise that to the 1/3 like we usually do. And if it helps, I'm going to write the secant squared theta over here just to show you this is our direct substitution, okay? It's all commutative. You don't need to do this, but I want you to see that this whole thing equals du. And if our u was tan theta, look at what we have. Oops, I'm sorry, that's a 1/3. And that's a pretty straightforward integral, okay? If I asked you to take the integral of this, well, your variable is u, and it's telling you to integrate with respect to u, so let's do it. You're going to add 1 to the exponent. That's going to give you u to the 4/3. And remember, it's 1 over your new exponent. Instead of giving yourself a complex fraction, 1 over a fraction is the reciprocal, plus c. And what did we need to do? Don't forget, we never started with u's, so we can't end with u's. And our u was up here. It was tan theta. And quite honestly, if they started with radical form, well, technically your answer should look like radical form. Apples to apples, oranges to oranges. So how would you do that? Well, let me see here. This would be a 3/4, and well, oh, I'm sorry, oh, I made that confusing. That's 4/3 like that. Well, the bottom is the root. It's the cubed root. And it's tan theta to the 4th. If you want to get technical, it goes right there, right? Plus c. And there's your answer. Let's take a look at another situation. What about this one? Now, if you were in class the other day, you probably saw this one. I did this one in most of my classes, but not all of them, and it's a great example, so I want to use it again in this video. And here we go. So most people look at that, I see a sine and a cosine, right? The first thing I see is I see sine theta and I see cosine theta, and well, don't you know that one of them is the derivative of the other? And the answer is yes. So maybe one of them could be our u, because when you take the derivative of u, you're looking for the derivative there. Now, if that doesn't stick out at you, you can rewrite this. By no means do you have to, but I want you to see something here. Cosine cubed theta is the same thing as cosine theta times cosine theta times cosine theta. And then, well, whether the sine theta is sitting up there in the numerator, if I just put it over here, sine theta d theta, well, that doesn't really make a difference, because if you multiply it, they're all the same thing. But you may notice this. Well, right now, this is the most common mistake. You're either going to do sine theta or cosine theta, because you need to get rid of the thetas. Let's see what happens if you were to call u sine theta, because that's one situation. This in white is going to be incorrect. I just want to show you what happens. Sometimes you have to guess on your u, and sometimes you're not correct. Here we go. So if that's the case, I could get rid of this. I could substitute that in with a u, but now I need to get rid of the cosine theta. So then when we do this, we do du, the derivative of u. We get cosine theta d theta. And well, notice how, well, first off, not only can I not do a direct substitution, because, well, look at this, I have 3 cosine thetas. I could substitute in 1 cosine theta, But not even in this case, because look, it's in the denominator. It's not even in the numerator. I'm looking for a cosine theta over 1. This is a 1 over cosine theta. That's not what we're looking for. So if that's the case, let's try the next one. Let's call cosine theta u instead of sine theta and see what happens for us. Right? All right, so now u equals cosine theta. So now if I call that my u, I could do du is negative sine theta, and d theta, and as we talked about the other day, the negative is not an issue. You can multiply or divide by a negative and just move it over to the other side. And with that case, ooh, look at what we can do here. This is a direct substitution. Okay, now even though it's not directly, we can't call it du, but we do know it's negative du, and well, we've done a bunch of these the other day, so the negative is a constant. We're going to throw that negative 1 out front. And when we substitute in, we get this. We get 1 over u cubed. That, my friends, is a pretty easy integral. So if well, before I integrate, let's call it u to the negative 3 du. Let's apply our power rule. And what happens is we need to add 1 to the exponent, which is going to give us u to the negative 2. We divide by our new exponent. Don't forget about your negative 1 in front. Plus c. All right, now that negative and negative is going to cancel. That's convenient. Notice here that is a negative 2 exponent, which is, we're going to put that downstairs to make that positive. So if directions ever tell you no negative exponents, you know what to do. So let's just rewrite this real quick. This is going to be, well, that would leave me with a 1 upstairs and a 2 down there, and our u squared plus c. What was u squared? Well, u is cosine theta, so it's cosine theta squared. You could also write this like this, cosine squared theta. Okay, these two are mathematically equivalent. Okay, on to the next one. Here, some may have seen this, others may not have. I've randomly did different problems here and there. So this one, sometimes you're going to see the dx up on the numerator there, and well, that's quite all right because, like I showed you just before, we can rewrite these things, and if I were to take the numerator out, we'd be left with this, and then you would just have x cubed times dx. Okay, cool. Well, that allows you almost to see what we're looking for, all right? We have something squared, but it's not just an x squared. That's another function in there squared. That's 1 plus x to the 4th squared. That's an inside function. And not only is that an inside function, but we have the variable piece of the derivative sitting right here, and we want that. We're not worried about the fact that we have the 4. We did that yesterday or the day before. Let's see what happens here. Inside function. U equals 1 plus x to the 4th. The derivative of u is 1 du. The derivative of 1 is 0. The derivative of x to the 4th is 4x to the 3rd dx. Since we don't have 4, we can do this like we've done before. And now, bam, bam, now we could do a direct substitution. X cubed dx, x cubed dx, well, that just equals this. So now 1/4 is the constant. It goes outside. This right here becomes 1 over u squared, and we're going to directly substitute in. We already put the 1/4 in front. There's your du. Before we jump into the integral, let's rewrite it like this, and now it's pretty darn easy. Okay, integrate. 1/4 just stays there. That's going to be multiplied at the end. And now for this part, we add 1 to the exponent. That's going to give us u to the negative 1. We divide by our new exponent, plus c. Let's combine this. Oh, here we have another negative exponent, so that's going to put the u value down there. So what we have is 1, and then, well, that is going to give you a negative 4. There's our u that we just put down in the denominator, plus c. And what was our u? The u was 1 plus x to the 4th. And there you have it. They also throw in the mix of homework problems, something like this, where you could totally use u substitution on the right term there, but you don't need to. And I'm going to show you why you don't need to. For some, I did this in class. But we also know this rule here. If you see this one, we have nothing to do with that. We have no substitution whatsoever to do with that one. So it might be beneficial to separate them out like this and take one integral at a time. There was a rule saying that, a property saying that it doesn't matter if you take the integral of f plus g. Well, it's the same as taking the integral of f plus the integral of g and then adding them up. So the reason I did that is because there's nothing special you need to do with this one. This just becomes you add 1 to the exponent and divide by the new exponent plus c. Right? And then over here, well, this is where you might want to tackle it with u substitution. So if you do, you want to show the u work, but it has nothing to do with this term over here. So you should separate them. All right, now I want to show you this. Now, for some in class, I showed you didn't. Sometimes if you see this, you don't need to always jump into u substitution. All right, let me show you what you can do on this one to avoid it. And it looks like this. Well, let's simplify. What is 3y times 3y? 3y times 3y is 9y squared, so that's really just 1 over 9y squared dy. And again, we didn't do the integral yet. This one we finished, right? The white there is done. So this is the same as the integral of 1/9 times this, right? Because if you multiply them, you get the same thing. And the reason I did that is because now here in blue, I could take the constant out, and I can make this y to the -2, and ta-da! We could have called, if you call u 3y and you continue in this fashion, you might want to try it. That would be dy, right, because the variable is y. You can totally get the same answer. You would do this and you would continue. So if you want to try it, you should get the same answer we just did. Or at least the same integral. We didn't get the answer yet. So again, I probably should have waited on this integral to do it all at once, but we already solved that one. That one is 1/3 y cubed, or y cubed over 3. Remember, when we integrate, we don't have to do plus c and plus c. I'm just going to do 1 plus c at the end here. Now in blue, let's integrate. I leave the constant. I add 1 to the exponent, which makes it a -1, and I divide by my new constant. And I guess I can write the plus c there a little bit closer. How about that? Let's clean it up. In white here, we now have 1/3 y cubed. This is going to be negative. Now this is a -1, so we got to put the y down there. So it's going to be 1 over 9y plus c. Right? And that would be our original function. All right, another example. This comes up often. I want to show you what happens when you do this. So this looks a little intimidating. And quite honestly, before I even jump into u substitution, I'm going to see if I can simplify this, because I know I can. We've gone over common denominators before. This is a common denominator. Oh, that's my highlighter. I wanted this, the pen. That's a common denominator. I can totally rewrite that like this. T over t to the 1/2. I'm going to call it t to the 1/2. You know we're taking derivatives. And then that is the same thing as a 9t squared all over the same thing. Right? Because it's a common denominator. If you were to subtract these two, you'll leave your common denominator. And then you add or subtract your numerator values. They're mathematically equivalent. But because I broke it into two terms now, I'm going to put them in parentheses. They both get a dt. If you do it this way, you can remember your exponent rules, or maybe not remember them, but if you do remember them, you can use them. When you have the same base and you're dividing, you subtract. So I didn't even take the integral yet. That's going to give you, so 2 over 2 minus 1 over 2 is a positive 1 over 2. This, well, this is a -9, right? That's just a 9 over 1. And then I have this. I have my t's. Well, 2 is the same as 4 over 2. So if I do 4 over 2 minus 1 over 2, that's going to give me a t with a 3 over 2. And as you can see, we do not need to use u substitution. All right. Another way you could have done this, I just want to show this method too, because there's so many varieties, and you may prefer to do it this way. If you don't like to divide, and if you remember multiplying, well, this is also mathematically equivalent to this. Again, this is t to the 1/2 over here, but if I put it up in front on the numerator, in the numerator, I make it negative, right? So that would be -1/2 dt. So if you prefer this way, well then, do you remember your exponent rules? When you multiply, you add the exponents. All right, well, if we add the exponents, this is a 1, so that's 2 over 2. And 2 over 2 minus 1 over 2, because you're adding a negative, is a t to the 1 over 2. And when you distribute here, well, that's a -9. And then this, well, 2 is the same as 4 over 2. So when you add a 4 over 2 and a -1 over 2, you get a positive 3 over 2 dt. And it doesn't matter how you do it, you end up with the exact same integral. So now let's integrate. This one, you are going to add 1 to the exponent. So it's going to be t to the 3/2 over 3/2, which is the same as multiplying by its reciprocal. Here's your -9. And then for this one, you add 1, which gives me a t to the 5/2. Oops, I should have made more room. And then in here, I have to multiply by its reciprocal 2/5 plus c. Let me just see here. So this is, let's write it in radical form. Why not? That would be 2/3. This is the square root of t cubed, right? I have to multiply these two first. Okay, so -9 times 2/5. That is going to be -18 over 5, right? You multiply the numerators and denominators. So that means I have a -18 over 5. And that is a square root of t to the 5th plus c. Let's take a look at this next one here. And we have an exponential function. And if you notice, we have another function in its exponent. We have a function inside of a function. I think we just found our u. U is the inside function. The derivative of u is du. That's nothing more than a constant. So the derivative of pi x becomes pi dx. The 2 goes away. Now we do have the dx we can substitute in, but we don't have the 1 over pi. I think you know what I'm about to do. It's just a constant. So you can multiply by its reciprocal and it goes on the other side. So now what we could do is a direct substitution. I'm going to substitute in for dx with a 1 over pi we put in front and the du we put right there. Our function now looks like this. That's a pretty easy integral. Remember, the derivative of e to the u would be e to the u. Therefore, the integral of e to the u would be e to the u plus c. Don't forget about your constant. We have that multiplied in the front. And we also never leave our u in there because we didn't start with u's. So let's make sure we put back what that u was. And there is our answer. How about another one? Okay, so this one over here, this has some exponentials in it as well, but it looks a little different. This step is not mandatory, but it does help a lot of people see what the derivative is. So let me rewrite this, and like I did before, I could just take that the numerator out, and it would look like that, all right? So right there, you can see that I have 1 over a fraction, but underneath that exponent is another function. Okay, this right here is a function inside of my rational function. And think about this. If we called u, here, let me do it down here. There's no reason to be up there. If I called u that inside function here, well, let's see what happens. You take the derivative of u, the 2 goes away, and you are left with e to the 3x times the derivative of the exponent, dx. Look at this. We have everything we need. We have the variable piece of the derivative. We don't have the constant, but you know what we're going to do. And if you do that, you could do a direct substitution. What is that? E to the 3x dx, okay? We're going to do this. We're going to substitute this in with this. 1/3 du. And now our integrand there is going to look like this. It is just 1 over u du. Remember, this one is going to be the ln function, and as a general reminder, if you divide by the new exponent, you're going to be dividing by 0. You can't divide by 0, so this is your one that's a little different. It's the ln, in this case, of u plus c. We talked about in class why those are absolute value, right? You need to have a positive value inside there. We looked at the graph at an earlier time. Now the u, we have to just substitute in there. So this is the ln of, what did we start off there? 2 plus e to the 3x plus c. There's your answer. Now this one down here, this one gets a little trickier. Okay, so this one, let's say this one here, let's talk about this. Now, the derivative of the top is, I'm just going to write it over here, it would be 4x plus 7. Well, I don't have 4x plus 7. The derivative of the bottom is 1. That's not going to help me get rid of the numerator. This one's tricky. I don't have the derivative of either one of them. What do? Well, sometimes you're left with synthetic division or long division because I can easily divide that out and then I would have something simpler to work with. All right? So when you don't know what to do and you can't find the u and you have a fraction, let's do this. Most people prefer synthetic division, so I'm going to do that. Don't forget you divide by the root, not the factor. Remember, if the factor is x minus 2, the root is x equals 2. And then what you do is you put your coefficients like so. The way you start is you bring down your first coefficient, and then you multiply these two things, you multiply. And that is going to give you a 4. That product goes here. You add up the columns, and then you repeat the process. You multiply, and that gives you 22. It goes there. You repeat it. You add up the column. 22 and a negative 3 is 19. This is your remainder, so you have 19 of your denominators left. You have 19 of x minus 2's left. And then this would be your constant, and this is the coefficient of your x term. So what we're left with is this. So now this integral right here is the same as this. I can integrate 2x plus 11 plus the remainder, dx. Now you may say that doesn't look good. Well, it's not that hard because, quite honestly, I only need to use u substitution on this one right here. So what I could do is this. I don't even have to separate them all out. Well, I'll just separate them all out. This is the same thing as 2x dx plus the integral of 11 dx plus the integral of 19 over x minus 2 dx. This one's easy, right? I have a constant 2. I'm going to add 1 to the exponent, and I divide by my new exponent. Plus, we only need 1 plus c at the end. Well, this is just 11, and since the variable is an x, that becomes 11x, because, again, the derivative of 11x is 11. Next. Now this one, I separated it out because this one we have to do u substitution on. And here we go. So, well, I could rewrite this like this. I could take out the 19 in front to make it simpler, so it's just 1 over x minus 2. Now, if that was just 1 over x, I would say the derivative is ln of x. But it's not 1 over x, it's 1 over x minus 2. So I'm going to call x minus 2 my u. You take the derivative of u, well, that just becomes 1 dx. Well, that's not too bad, because now I could do this. That becomes du, right? dx equals du. And this is just 1 over u. And I have my 19 on the outside there. Okay. I'm still finishing the integral here before we add up these terms. So now here I have a 19 on the outside. This becomes the ln of u with the absolute value signs. We talked about that. Plus c. And our u was up here. It was x minus 2. So the final answer here in white, these cancel. I have an x squared from that first one. I have an 11x from the second one. And the third term is this. Plus c. Here's another common situation you're going to come across. It's called change of variables. You'll see why. We're going to change some variables. This yellow integral, whoops, sorry about that. This yellow integral is not a change of variable. This is just a reminder. This is going to be a regular u substitution. So just regular u sub. And, well, my inside function, I have a square root. And inside my square root, I have another function. I have a 2x minus 1. So if I were to call the inside function u, the derivative of u becomes 2 dx. And we can do this. So in order to do a direct substitution for dx, we're going to call it 1/2 du. And now we can take our u, and what we're left with is this. And in order to save a little board space, the square root of u, we're going to integrate. So I'm going to give myself a little exponent there. Now let's go ahead. The 1/2 stays. What you do is you add 1 to the exponent, which gives us u to the 3/2. Divided by 3/2, which is the same as multiplying by the reciprocal. Let me just make that u a little bit lower so it makes more sense. Okay. Plus c. those 2's cancel up and down, so we just have a 1/3 in front. Let's rewrite that. The denominator is the root. It's a square root. And there's my u cubed. Our u was up here. It was 2x minus 1 plus c. There's your function. Now let's look at this one over here in green. And notice how similar it is. The only difference is we have an x involved. So, well, look at what we have, a dilemma, because if we go ahead and do the same thing, right, I have 2x minus 1 under the radical, well, we would do that, but we don't get 2x. It's not like I can get rid of that x. I can't substitute and get rid of it. So I would do this, and, well, let me see. I guess the most I can do would be this. I still don't know what to do with that x. This would be, well, here, I know that's going to be u to the 1/2. And if we did this thing right here, we'd have a 1/2 in front, and we'd have a du. And as you probably noticed, this is nearly identical to this white integral over here. Just this one we can do, though, right? That was u sub. We subbed in, and we can do it. This one, we have a problem. We have an x left over that I don't know what to do. I can't get rid of. Well, I do know what to do, but does anyone have any ideas? I'm wondering if anyone might have thought of this. So remember what we said. We said that our u value is 2x minus 1. Well, remember our goal here. Our goal is to substitute all x's and dx's with u's and du's. We can do that. Just solve for x. So we know that x is equal to u plus 1 divided by 2. So what if we just call it this? U plus 1 over 2 times u to the 1/2 over 1, just as I'm going to multiply these. And, well, I'm allowed to do that. And that's called changing the variable. We just changed the variable. If you know what u is in terms of x, well, then you can figure out what x is in terms of u. And that's what we just did. And then let's combine this now, because I can distribute this and just give myself a couple terms here. That would be, remember, you add the exponents, so that would be a u to the 3/2. And then when you distribute, 1 times anything is itself. And it's all over 2. I'm going to take that out, though. I just want to do one thing at a time. Now, I could have done this before, but I didn't want to do 2 things at once. Now I take that out, and now I'm left with this. And now we can integrate. All right, we have a 1/4 out front. We'll multiply that at the end. And now let's do this. We're going to add 1 to the exponent, which gives that a, let me do that, a u to the 5/2. And then we divide by 5/2, which is the same as multiplying by the reciprocal. Actually, I don't need that. Now let's do the next one, plus. I have, I'm going to add 1, which gives me u to the 3/2. And then I have to remember to multiply by the reciprocal, which is 2/3. And that is going to be plus c. You don't necessarily have to do this. You could leave it out, but most people will distribute this. And then what is that? That's 2 over 20, so that's 1 over 10. And then you have your u to the 5/2. I'll clean that u up in a moment. Now when we distribute here, that's going to be 2 over 12. 2 over 12 is 1/6. I'll take care of the u in a moment. That's 3/2. And then you don't have to call this 1/4 plus 1/4 c. We talked about that. Any random constant times 1/4 is still any random constant. I am going to convert these to a radical form because we started with radicals up here, right? So it would look like this. This is, you can leave this out front, and we have our u value. It's a square root raised to the 5th. Our u value was 2x plus 1. Next term is plus 1/6. The denominator is a 2. It's a square root, and the u value is cubed. Our u value is 2x plus 1. Don't forget your plus c, and we have our answer. This one here is rather tricky, so let's look at this one. Whenever you can clean these things up, I highly recommend it. So the first thing I'm going to notice is I do have a 1/3 that is a constant, I can take that 1/3 out, which is going to at least make it down to this. It looks a little bit easier on the eye. And, well, now we have inside this integral, we have really two choices, right? Are we going to call u x squared, or are we going to call u 1 minus x? I don't know. Well, which would be our better bet? This one, if we took the derivative, would look like this. It would be, what, negative dx. That's not going to help us get rid of the x squared. What about this? Well, actually, let me not cross it out. This one, well, if we took the derivative of this one, that's going to leave us with a 2x dx, and, well, that helps us get rid of this, but I can't get rid of 1 minus x underneath, so that's not going to work for us, okay? So what if we go ahead and do this? Similar to our last example, if you know that u is the same thing as 1 minus x, well then we can do this. We can call x the same as 1 minus u. And that changing of the variable right there will allow us to get all u's and du's. Because now we have x squared, but x is 1 minus u. Next term, well, 1 minus x was u. And, oh, don't forget, over here we said du equals negative dx. So I have to substitute in dx with a negative du. I'll put the negative in front like we always do. And what we have is negative 1/3 on the outside, 1 minus u times 1 minus u times u to the 1/2. And all of this can be multiplied. So we're going to multiply this. In the interest of time, I did this already. So when you multiply these three things together, you're going to get this. You're going to get u to the 1/2 minus 2u to the 3/2 plus u to the 5/2 du. Let's finish her up. We have a negative 1/3 on the outside, and now let's integrate. This term, when you add 1, you get u to the 3/2 divided by 3/2, which is the same as multiplying by the reciprocal. Over here, when you add 1, you get 5/2. Don't forget your negative 2, and then we have a u. Wait, I'm going to do that so we have room. I have u, I have a 5/2, and then we multiply by the reciprocal. Plus, this one over here, when you add 1, you get 7/2. So we have a u raised to 7/2 times the reciprocal. Plus c, but now I'll write it like that because, as we keep saying, we don't have to distribute the negative 1/3 to the c. It's just going to be another random constant, so just leave it at the end. We do need to distribute it here, though. We have this term and this term and this term. So the first one is negative 2/9. That is a square root. It's u to the 3rd. This multiplication, that gives you negative 4/5, but then don't forget you have to distribute this, and that's going to make it positive 4/15. Positive 4/15. The next, that is a square root, and I have a u raised to the 5th. The next term, this is a 2/7 in front. That's a square root, and I have my u value raised to the 7th plus c. Our u value was up there. It was 1 minus x. And here, whoops, 1 minus x. That is our answer. I notice here in the answer keys that they even go farther in the textbooks. They take out the perfect squares here. But I will be honest with you, if you can get to this point, I would be very happy.